All right, so in this video, we are going to wrap up valence bond theory and hybrid orbitals and all that stuff and apply those concepts to talking about a particular molecule, in this case, acetone. So what we want to do for acetone, CH3 to CO, is we want to be able to draw the Lewis structure and identify what types of bonds and orbitals are present. So to begin with, we're going to start by drawing our Lewis structure. Now, we've done this for acetone before, but let's make sure we don't miss anything. We've got 3 carbons, we've got 6 hydrogens, and we have 1 oxygen. So we have 3 times 4, 6 times 1, and another 6 electrons. So 6 plus 6 is 12, 12 plus 12 is 24 electrons. We're going to start by putting 1 carbon in the center, and because of how this is written up here, we're going to put 1 carbon on one side, 1 carbon on the other. Those carbons are each going to have 3 hydrogens because we see those in the group in the condensed molecular formula. And then we've only got 1 carbon that doesn't have a full octet. We're going to attach the oxygen to that and check how many electrons we've used up. We got 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 so far, which means we're going to have 6 left. Those 6 are going to go up here. 2, 4, 6. Carbon's not happy. We want to give it a full octet. So we're going to erase 2 off the top and move those into a double bond, and that gives us our structure for acetone. All right, now honestly, from right here you can do all of the bond type identification that you need to do, because remember, your first bond between any 2 atoms is going to be a sigma bond. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds. And I'm going to have 1 bond that I didn't circle, so therefore I've got 1 pi bond. So those are my types of bonds that I have. But what orbitals make up each one of these? So this is where we kind of have to talk about hybridization. All right, so I'm going to sketch this again real quick. I've got my CH3, CO, CH3. My 2 terminal carbons, so we'll call these 1, 2, and 3. So 1 and 3 are both going to be sp3 hybridized. Carbon 2 is going to be sp2 hybridized. I know that from the number of electron groups that I got, right? I'm either AX4 or AX3 for my ax notation in the center. Right? 3 electron groups means I need to have 3 bonding orbitals there to form my sigma bonds. So I'm going to have sp2, 4 electron groups, 4 bonding areas, sp3. Right, so we could then at this point draw all the orbitals and show them. And I got that on the next page set up a little bit in advance. Right, so here we can see all the sigma bonds as well as all the individual orbitals. Right, here's my central carbon, right, that has the double bond to it, and we can see that it is forming a sigma bond here with the oxygen and a sigma bond with each of those carbons. Each of the carbons is forming a sigma bond with each of the hydrogens that's attached to it. Up here, forming no bonds at all, we've got the 2 lone pairs. They're still hanging out in sp2 orbitals. That's important to remember, right? Lone pairs have to go somewhere. We need to have an orbital to put them into. Now, this image on the left here does not show our pi bonds, which is what we're going to show over here. We're going to show that pi bond in the plane of the page, so just flat on the paper, and it takes up both the left and right sides. And we can see the 2 CH3 groups coming out of the page and going back into the page. And then we see that one pi bond that we've got there. So we've got all the sigma bonds, we've got all the pi bonds. One thing I don't like about this isn't labeled, that this is a p orbital. We do want to make sure we highlight the types of orbitals that we're using. Pi bonds are going to be formed by our p orbitals. Let's take a look at another example. Here's CH2NH. All right, now CH2NH, I'm going to have a carbon, I'm going to have a hydrogen, I'm going to have 3 of them, and I'm going to have a nitrogen. Right, so we got 4, 3 times 1, and 5. So what do we end up with here? 8, 9, 10, 11, 12 electrons. I have my carbon attached to 2 hydrogens, attached to a nitrogen, attached to a hydrogen. I've used up 2, 4, 6, 8. I got 4 electrons left. I would add both to those nitrogen. Carbon's not particularly happy, so let's erase those, move it back. There is my overall structure for this molecule, CH2NH. Again, we can say, okay, my carbon and my nitrogen, my carbon is AX3, my nitrogen is also AX3. They have the same electron geometry, which means we would expect both of them to be sp2 hybridized. The carbon, right, and we can sort of draw our geometries here, and then the nitrogen, where that other third body is the lone pair. What does this look like in terms of my orbitals? Right, so I got a carbon, and I got my nitrogen. There's my sigma bond, right, formed by my two sp2 orbitals. Here's my hydrogen. It's got an s orbital. All right, so we can see our sigma bonds here in red. All right, now what about my pi bond? All right, my pi bond, let's do this in a different color, make it look a little more obvious. All right, I've drawn this all flat on the plane of the paper, so really my pi bond would come straight out towards us and then kind of go back away from us into the plane of the page, and that would be my pi bond right there. And those would be made of p orbitals. So again, the things I like about this one is that we've got a series of sigma bonds, we've got one pi bond, and we have a lone pair here that's also adjacent to that pi system. All right, one last thing I want to talk about in terms of pi bonds is that pi bonds don't rotate. Sigma bonds do. If I've got a carbon and it's attached to another carbon and that's all that's there, I can kind of treat this end like a pinwheel and I could spin it around and around and around a sigma bond. A pi bond, though, it's got basically two bars, one above and one below. And if I twist them, right, if I take these two things and I try to twist one end, if I don't twist the other end, eventually I've got to break the bond. Right? One of these would have to, at least one would have to shatter, and I'd start pivoting around the other one. Right? So for this reason, systems with pi bonds in them don't freely interconvert in a lot of cases. If you add enough energy, can you break the pi bond up and make them rotate? Sure, right? And we'll talk about that way later on down the road. But a good thing to think about right now is that pi bonds don't spin. Sigma bonds spin. All right? Sigma is your first single bond and also spins. So again, those sort of S sounds go together. So we can't convert pi bonds because we'd have to break them, or we can't rotate pi bonds because we have to break them, but we can spin around those sigma bonds as much as we want. This becomes really important later when we talk about molecular geometry and stereoisomerism and other things that become super important in talk about equilibrium and bond making and breaking in organic chemistry. So keep that in mind as you go down the road, that this is something we'll come back and loop back to. All right, thanks for hanging around, and we'll catch you in the next one.